Look around the room you're in right now. The light reaching your eyes, the screen you're staring at, the invisible signal carrying this video into your hands. Every bit of it, light, radio, electricity, magnetism, the warmth of the sun on your skin, obeys the same 4 short lines of mathematics. 4 equations. You could write all of them on a napkin, and inside that napkin is the entire behavior of light itself. They are, by wide agreement, the most elegant equations ever written. When the physicist Ludwig Boltzmann first saw them, he quoted Goethe and asked, "Was it a god who wrote these lines?" This is the story of those 4 lines. How a quiet Scotsman took the most mysterious forces in nature and in a single stroke revealed that they were never separate at all. And how, buried inside his mathematics, he found light and predicted a world he would never live to see. The story begins not with Maxwell, but with a man who could barely do algebra. Michael Faraday was a bookbinder's apprentice who became the greatest experimentalist of his age, and he had almost no mathematical training at all. What he had instead was an imagination. Faraday played with magnets and wires and electric sparks, and he began to see something no equation had captured. He pictured invisible lines threading through space, around every magnet, around every charge, real, physical lines of force filling the emptiness. He called it a field. To the mathematicians of his day, this was almost embarrassing. Where were the numbers? Where was the proof? Faraday could feel the field in his hands, but he could not write it down. Electricity and magnetism sat there like 2 strangers who seemed, somehow, to be related. A compass needle twitching near a wire, a spark leaping when a magnet moved, but nobody could say exactly how or why. It would take a mind fluent in both physics and pure mathematics to finish what Faraday could only imagine. That mind belonged to James Clerk Maxwell, born in Scotland in 1831. Where Faraday saw pictures, Maxwell saw equations, and crucially, he took Faraday's strange invisible fields completely seriously. He set himself a task that sounds almost impossible: to translate Faraday's imagination into airtight mathematics, to take the lines of force and write down exactly how they behave. And as Maxwell worked, gathering up everything that was known about electricity and magnetism, he found he could compress all of it, every experiment, every law, a century of tinkering, into a small set of equations describing how electric and magnetic fields are born, how they twist, and how they push on one another. He was doing for electricity and magnetism what Newton had done for motion, replacing a pile of separate rules with a single, unified language. But when he assembled the pieces, Maxwell noticed something was missing. The equations, as they stood, did not quite balance, and fixing that imbalance would change the world. Let's actually look at what the 4 laws say, not the symbols, the meaning. The first law is about electricity. It says that electric charge is a source. A positive charge sprays invisible field lines outward in every direction, and a negative charge drinks them in. Wherever there is charge, the electric field has a beginning and an end. Simple enough. The second law is about magnetism, and it says something stranger and more beautiful. It says magnetism has no sources at all. There is no such thing as a lone North Pole. Take a bar magnet, cut it in half, and you don't get a north and a south, you get 2 smaller magnets, each with both poles again. Cut those, and it happens again, forever. Magnetic field lines never begin and never end. They only ever form closed loops. 2 laws, and already a deep asymmetry between electricity and magnetism is staring back at us. Maxwell was about to discover that the universe hides a much deeper symmetry underneath. The third and fourth laws are where everything comes alive, because they describe how the 2 fields talk to each other. The third law is Faraday's great discovery, written at last in mathematics. A changing magnetic field creates an electric field. Move a magnet through a coil of wire, and a current flows, out of nothing, out of pure change. This one law runs every power plant on Earth. The fourth law was, at first, only half true. It said that an electric current creates a magnetic field. An electrical wire wraps itself in magnetism. True, and known for decades. But Maxwell stared at his four equations and saw the flaw. The symmetry was broken. A changing magnetic field made an electric field. So why, he asked, shouldn't a changing electric field make a magnetic field? Nothing in the experiments demanded it. But the mathematics ached for it. So Maxwell added one new term, a piece he called the displacement current, a term that no experiment had asked for, put there because the equations were more beautiful with it than without. It was one of the boldest acts of faith in the history of science, and it was correct. Now watch what that one added term does. Put the third and fourth laws side by side. A changing magnetic field creates an electric field, and a changing electric field, Maxwell's new piece, creates a magnetic field. Do you see the loop? Imagine a magnetic field that suddenly changes. It gives birth to an electric field. But that new electric field is itself changing, so it gives birth to a magnetic field. And that magnetic field is changing, so it makes another electric field a little further on. Each field, by dying, creates the next. The disturbance does not need a wire. It does not need air or water or any material at all. It carries itself, hand over hand, electric to magnetic to electric, leapfrogging through completely empty space, a wave that builds the very track it runs on. Maxwell had found a wave that could travel through nothing, forever. And now the only question was, how fast does it go? Here is the moment that should give you chills. Maxwell's equations didn't just predict this self-sustaining wave. They set its speed. And that speed was fixed entirely by two numbers already sitting in the equations. One measuring the strength of electricity, the other the strength of magnetism. Two constants that had been measured in laboratories, by men rubbing amber and winding coils, with nothing to do with light whatsoever. Maxwell took those two purely electrical and magnetic numbers, combined them as his equations demanded, and out came a speed. He worked it out. And the number that appeared was about 300,000 kilometers per second, almost exactly the measured speed of light. Sit with how strange that is. He was studying magnets and currents. He was not studying light. And light fell out of the equations anyway. There was only one possible conclusion, and Maxwell had the courage to write it down. Light itself is an electromagnetic wave. The glow of the sun, the color of the sky, the beam from a candle, all of it is this same self-building dance of electric and magnetic fields, discovered at the bottom of equations about sparks and compasses. Electricity, magnetism, and light, three great mysteries, turned out to be one single thing. And if light was just one electromagnetic wave, then the equations quietly promised something enormous. Light could not possibly be the only one. Nothing in the mathematics singled out the colors our eyes happen to see. The same wave could vibrate slower or faster, without limit. An entire spectrum of invisible light stretching out on both sides of the rainbow. Below the red, waves too slow for the eye. Above the violet, waves too fast. Maxwell's equations predicted a whole ocean of invisible radiation that nobody had ever detected. It was a staggering claim from pure mathematics. And Maxwell died in 1879, at just 48, without ever seeing it tested. Then, 8 years later, a young German physicist named Heinrich Hertz built a spark gap in his laboratory and, in 1887 and 1888, produced and caught these invisible waves out of thin air, exactly where Maxwell's mathematics said they would be. The prediction was real. Hertz had made the first radio waves. He thought them a beautiful curiosity of no practical use, and he too died young, at 36. But others saw further. Those invisible waves became radio, then television, then radar, then the signal in your pocket. Today we call the whole invisible ocean by its parts: radio, microwave, infrared, ultraviolet, X-ray, gamma ray. Every one of them is the same wave Maxwell found. Your Wi-Fi and a gamma ray from a dying star are the same phenomenon, singing at different pitches. So why do we call them the most elegant equations ever written? Here is the surprise. When Maxwell first published them, they weren't 4 equations at all. They were 20, a sprawling thicket of 20 equations in 20 variables, dense and hard to read. The beautiful, compact form the whole world now knows came later, in 1884, when a brilliant and reclusive self-taught engineer named Oliver Heaviside, working alongside similar ideas from Gibbs and from Hertz, rebuilt them using the language of vectors. 20 equations collapsed into 4. And in that compression, the hidden symmetry finally shone through. Electricity and magnetism standing as near mirror images, light falling out of the middle, 4 lines that contain radio, and heat, and every color, and the reason you can see it all. This is what physicists mean by elegance, not decoration, but staggering power folded into staggering simplicity. It is the same beauty as the most beautiful equation in mathematics, e to the I pi plus 1 equals 0, the sense that you are not reading a human invention, but overhearing a rule the universe was already obeying. Was it a God who wrote these lines? Richard Feynman once said that 10,000 years from now, when people look back on our century, the American Civil War will fade into a local squabble, and the event that will still matter, the one that truly changed the world, will be Maxwell's discovery of the laws of electrodynamics. He may be right. Every wireless thing you own, every screen, every scan in every hospital, the light you are reading by, the sunlight that grows your food, all of it runs on 4 lines a Scotsman wrote down because they were too beautiful to leave unbalanced. He unified electricity, magnetism, and light. He predicted an invisible universe and was proven right after his death. And he did it not by measuring harder, but by trusting that the mathematics of nature would be symmetric, and following that faith 1 term further than the evidence required. That is the deepest lesson these 4 lines teach, that the universe, at its foundation, appears to be written in a language of almost unreasonable beauty, and that if you learn to read it, it will tell you things no experiment has yet dared to ask. If seeing why the world works means more to you than being told that it does, subscribe, because that is the only kind of story we tell here. I'll see you in the next dimension.